Assalamualaikum and hi. These are our team members. First, Rabiatul Adawiyah binti Sufyan. Second, Shifa binti Muhammad Syahir. Third, Nur Fazrun Akila binti Muhammad Fazil. And the fourth is Nur Atira Nabiha binti Muhammad Zainuddin. This is our project introduction. What is this project about? This project is about creating a model that can recognize and classify image of flag from different countries using a deep learning technique called convolutional neural networks. The model will learn to identify flags and categorize them correctly. Why we done this project? This project will help you to learn how to apply machine learning in real world, like image recognition. It also shows how to use CNN, which are great at recognizing pattern in image. By doing this project, you get hands-on experience with data preprocessing, model training, and evaluation, all which are the essential skill in this field of AI and machine learning. First, we need to import the necessary libraries. TensorFlow and Keras will be used for building and training the model. NumPy help with numerical operation. Matplotlib is used for visualizing data, and OS help in handling bypass. We also import compute class weight for balancing dataset. Next, we mount Google Drive to access the dataset stored there. In Collab, this allows us to directly use files from Google Drive. Next, we define the base directory where our image are stored and set some key parameters. Image size. The size of image will be resized. Batch size, the number of image processed at once, and auto-tune, a TensorFlow optimization parameter that helps in efficient data loading. Next, we load the dataset from directory. The dataset are split into training and validation. Set using 80 to 20 split. The image are resized to predefined image, which is image size. And then we store and print the class name detected as in dataset. The name correspond to different categories of image in our dataset. After that, we define a function pre-processing image. The image are normalized to range of 0, 1 by dividing the pixel value by 255. Level are converted into hard encoding to be used in classification.
Hi and Assalamualaikum, I'm Shifa binti Muhammad Syahir and now I'll be explaining about model compilation and development. For the data augmentation is a technique used to artificially expand our training dataset by applying random transformations to the images. This helps prevent overfitting and ensures that our model learns to recognize patterns in a variety of conditions rather than memorizing specific details from the training dataset. In our case, we applied two main augmentation techniques, which is random rotation and random zoom. For random rotation 0.1, this means that each image in our dataset can be randomly rotated by up to 10%. This is useful because in real-world scenarios, images of flags might not always be perfectly aligned. They could be slightly tilted due to the way they were captured or displayed. By applying random rotations, our model learns to recognize flags even when they are not in their ideal orientation. Next is random zoom 0.1. This means that our images can be randomly zoomed in or out by up to 10%. Sometimes images of the same flag may appear at different sizes depending on the camera distance or resolution. By applying this, our model becomes more robust and can recognize flags at different scales. For model development phase, we are using CNN, Convolutional Neural Network, which is a deep learning model specifically designed for image classification. CNN works by detecting patterns in images such as edges, textures, and shapes, and it gradually learns more complex features as the data moves through the network. Based on our coding, the first convolutional layer has 32 filters of size 33 and use ReLU activation function. This means that it detects simple patterns in the images like edges and colors. Then, a max pooling layer follows to reduce the size of the image while retaining the important details. The second and the third convolutional layers increase the number of filters to 64 and 128, respectively. These layers allow the model to learn more complex features such as symbols or letters on flags. We then apply dropout with a rate of 0.3, meaning 30% of the neurons are randomly turned off during training. This prevents the model from memorizing the training data and forces it to learn general patterns instead. After that, we flatten the output from the convolutional layers and pass it through a fully connected dense layer with 256 neurons, followed by the final softmax output layer. The softmax activation function ensures that our model assigns probabilities to different flag categories, allowing it to make accurate classifications. Once the model is built, the next step is compilation. Model compilation is where we define the loss function, optimizer, and evaluation metrics. Adam optimizer, which is widely used in deep learning because it adapts the learning rate during training, making the process more efficient. Since this is a multi-class classification problem, we use categorical cross-entropy as the loss function. This measures the difference between the predicted and actual labels and updates the model accordingly. Lastly, we track accuracy as our performance metrics, as we want to measure how well the model is classifying flags.
Akila, and I'll be explaining about training and evaluation part. So for the first one, I'll explain about handling class imbalance with class weights. I think why do we need class weights is because we may have an imbalanced data set, meaning some classes have more samples than others. So we need to handle it properly, and to fix this, we use class weighting. So for the first one, extract labels, we initialize an labels list as an empty list labels, and then we loop through the data set and extract labels from each batch. And then since the labels might be in NumPy, so we convert them to list using NumPy.toList. And then for the second one, ensure labels are integers. We convert all labels to integers to avoid potential type mismatch when computing class weights. And for the convert class weight to dictionary, the computed weights are stored as an array, so we convert them into a dictionary because this makes it easier to map each class to its corresponding weight. And then for the conclusion for this one, by assigning class weights, we help the model treat all classes fairly and improving its overall performance on imbalanced dataset. Moving on to the next one, for this part, we often deal with large datasets, and if we don't pre-process and optimize our data, the training process can become slow and inefficient. That's where operations like mapping, caching, shuffling, and prefetching come in. This helps faster training by avoiding bottlenecks in data loading. And this code is an essential part of optimizing the deep learning workflow, and we ensure smooth and efficient model training. For this part, which is train the model, this one we are training our deep learning model using TensorFlow model.fit function. So for this one, train underscore ds means the training dataset used for learning epoch 15, which means the model trains for 15 complete passes through the dataset, and for the validation data, it evaluates its performance on the validation dataset after each epoch. So epoch count is 115, means it's the first epoch out of 15. Time per step, which is 31 3x per step, indicates how long each step takes. And then for the training accuracy, measures how well the model is performing on the training dataset. And also we have training loss, validation accuracy, and also validation loss. So the training, this process helps the model learn patterns from the data. After training, we can evaluate its performance further and fine-tune if needed. For this part, the model is a complex structure designed to handle image data, ultimately classifying inputs into 5 classes. The use of these convolutional layers, max pooling, and dense connections make it powerful for image recognition. For the initial layers, which is layer 1, pusher will be none 180, 180, and 32, and for the filters, it will be 32, kernel size will be 3, moving to max pooling 2D layer and the others also.
Assalamualaikum, my name is Nur Atirana Biha, and I'm going to continue the presentation. In this part, we implement a coefficient matrix to evaluate the model's performance. The matrix compares the true levels with the predicted one and show how well the model classifies each flag. The coefficient matrix is displayed visually to help identify area where the model is performing well or struggling. Here we have the coefficient matrix that evaluates our classification model performance. The row represent the actual class levels, while the column represent the predicted levels. The diagonal values indicate correct prediction, meaning the model classifies those instances accurately, while the off-diagonal values show misclassification, where the model indicates the wrong class. The intensity of the color represents the frequency, which darker shades indicate higher value. From this matrix, we can see those predictions are correct, especially for Belgium, which has the highest accuracy. However, some misclassification exists, particularly in Denmark, where some instances were wrongly classified as Austria and Ireland. This conversion metric helps us understand where our model performs well and if there is an improvement are needed. Next, we are going to testing model with random sample. Here, we randomly selected a few images from the validation dataset to test how the model performs on unseen data. The model predicts the flag, and the true and predicted levels are shown with the prediction confidence. This gives a clear view of how well the model generalizes. So here we have the testing model with random sample from the classes. As we can see, most predictions are true and correct, where the predicted percentage is higher than 90%. For this part, we will add interactivity by allowing users to upload their own flag image. Once an image is uploaded, the model predicts the flag and shows the prediction confidence. This makes the model easy to use and practical for real-time application. As you can see here, there is a button upload here where user can choose the file and image from their file. So here I upload 3 images, which is Denmark, Bulgaria, and Belgium. As you can see, it predicts the country correctly, and the prediction confidence is 100%. Lastly, after training the model, I save it for future use. This allows anyone to load the trained model later without retraining it. I also provide a download option so the model can be easily shared or deployed. For this case, I download the model to use it later for GUI. So here is the GUI of our flag recognition app. This interface is built using Streamlit and allow user to upload an image of a flag for classification. At the top, the title is Flag Recognition App, and then below, user can upload an image file in JPG or PNG format. So I'm going to upload an image. So once the image is uploaded, it is displayed on the screen for reference. The system then processes the image, resize it, and normalize it before sending it to the trained model for classification. So after processing it, the predicted country name is shown along with the confidence percentage. As you can see, it predicts as Ireland, and the confidence percentage is 100%.
So I'm going to upload other image from other countries. So as you can see, it does predict it as Austria, and the confidence percentage is 99.98%. And here it predicted as Belgium, and the confidence percentage is 100%. So here it predicts as Bulgaria, and the confidence percentage is 100%. Here it predicts as Denmark, and the confidence percentage is 100%. So as you can see, it provides user with clear and immediate feedback. Hence, it's shown that the interface is simple and user-friendly, as well as efficiently presents the model output.